Okay, so I apologize for the fact that the first time I did this lecture, it did not record properly, or at least it didn't all record properly, so we're redoing it. So here we go. We're talking about cardiovascular adjustments to exercise, and so here are the couple of things that we're going to talk about. And really, we're going to focus on VO2 max here. So if you remember, VO2 max is the body's ability to maximally take in oxygen. In other words, how much oxygen can your body take in and use? All right, this is different from the amount of oxygen that comes into your body. It's how much is your body actually using. Remember, when you breathe out, there is lots of oxygen in that air. And a big reason of that is because you're not using everything that you're bringing in. All right, so I want you to look at this picture here, and there's a couple things going on. So we're going to divide this in half. And so we've got rest and we've got exercise. Okay, so what you can think of is this is in the veins and this is in the arteries. Okay, so just focus on the top half right now. So let's just say that at rest, we've got blood flow. We'll just say each one of those circles represents a liter of blood. Okay, and so that liter of blood contains X amount of oxygen, and what's ultimately happening is that we're only using about 25% of the available oxygen at rest. Okay, but when it comes to exercise, we will use many, many times more oxygen than we will at rest, and it can be 12 or even 15. All right, so how do we accommodate for this? Okay, so what happens is we can increase our cardiac output by 4 or 5 times, and so now instead of having 4 circles, we've got 16. And then the other thing is that we're going to extract more oxygen out of our bloodstream and use it. And so instead of only extracting 25%, which is what's going on here, we're actually extracting 75%. And so this is how we increase our VO2 max, or increase our VO2. Okay, we deliver more blood and then we pull more oxygen out of that blood. Now, when it comes to cardiac output, remember exercise plays a big role in that. Resting heart rate can be as low as high 20s, typically in the 60s, but it can be as low as 28 up to 100. I know that this was an exam question that Trevor asked you about what somebody's resting heart rate was. Now, your heart rate max doesn't really change, except for other than the fact that it decreases slowly over time. So I see students come in and do a VO2 max test or even a submax test, and their heart rate's in the 180s, and they still go for a little while. Whereas if I'm at 180, I'm about done. That's about as much as my heart can do these days. And so the way that this happens is with sympathetic activity. However, there's a potential problem with this, and this comes to filling time. So what happens to filling time during exercise? We know that heart rate goes up. So what's going to happen to filling time? And what happens is that it goes down. So how would that affect stroke volume and cardiac output? Well, reduced filling time is going to decrease stroke volume, which would decrease cardiac output. At the very minimum, it would prevent cardiac output from increasing. So how can we compensate for this? Well, we can increase our heart rate, but that might not be enough. Okay, if our heart rate increases by 10%, let's say our stroke volume decreases by 10%, our cardiac output remains the same. We need a way to be able to accommodate or provide more blood, more oxygen. So how do we do this? I had a good conversation on Friday with one of you about this, and so we're going to get into this just in a little bit, and I think a little bit more later here. So remember end diastolic volume. End diastolic volume is the pressure that's in the ventricle before contraction, and this pressure comes from the blood that's in the ventricle. There are 2 ways we can increase pressure in the heart. We can put more blood in it, or we can contract harder. As you can see from this figure, this is the Frank-Starling relationship. As we increase end diastolic volume right here, what happens is our heart contracts with a greater force, so we have a greater stroke volume. Okay? And so it's not enough just to contract harder, like just putting a whole bunch of epinephrine. We still need to be able to get blood back in there. And so we're going to talk about that later on, not in this video, but we've got to have a way to increase venous return. Because if all I do is increase my contractility for a beat or two, well, that's great, but eventually I'm going to run out of blood if I don't increase the amount that's coming back to my heart. But I want to focus real quick on the sympathetic nervous system. What does the sympathetic nervous system do? Well, it increases heart rate, but it also increases stroke volume by increasing the contraction strength. And so what this means is, yeah, we'll increase the strength of contraction, but what's really interesting is our end diastolic volume, so the amount of blood before contraction, is constant, but all that's happening is we're increasing the amount of blood that's going out, so we're increasing our stroke volume, which leads to a decrease in end systolic volume. So how can we affect cardiac output during exercise? Well, we've got a couple of ways, right? So we've got this table here, or this flow chart, I guess is a way to look at it, and there's a couple of different ways. So remember, ejection fraction is the percentage of blood that's leaving the heart with every contraction. Okay, let's just say normally our ejection fraction is 52% with a stroke volume of 70 mils. Well, if I have normal filling and I have sympathetic stimulation, my stroke volume will increase up to 100. Okay, my ejection fraction is 74. Now, let's just think about this for a minute. So I'm going to try and do some math here. So let's just say that max stroke volume is 200, max heart rate is 200 because you guys are young and fit, okay? And we do 70 mils a minute, or 70 mils a beat. That actually gives us 14,000, that's 14 liters per minute, okay? But that's really making your heart work extremely, extremely hard, okay? If we increase our stroke volume to 100 mils, well, that 14 liters now becomes whatever 200 times 1,000 is, so we're getting up to 20 liters, okay? So I'm hoping that I'm doing this math right. That gives us 20 liters a minute, which is a really, really high amount, okay? These aren't typical values, but I'm trying to make a point here. But now, if we have increased filling and the sympathetic stimulation, if we take our max heart rate of 200 and multiply that by 140, that gets us up to 28 liters a minute, which would be an insane amount of blood or insanely high cardiac output. Now, that's not typically what happens, or we don't have this maximum stroke volume like this. But what we can do, another way to look at this, is that we can take this 140 mils, and if we just have a heart rate of 100, that gets us that 14 liters that we'd have to hit, where we'd have to be at heart rate max, okay? And so it's important to have this sympathetic stimulation, but it's also important to have increased filling. So I want you to think about, well, how can we have increased filling? Because that's how we're going to end up getting the most bang for our buck with stroke volume. Okay, so training with or cardiac output during exercise, notice that this is intensity on the x-axis, but we have a stroke volume on the y-axis. Notice that we get to about 50-60%, and what happens is we essentially kind of tap out with our stroke volume. Okay, there comes a point where we can't get more blood into our heart. Now look at this same figure. This time instead of intensity, we've got heart rate, and what's happening is that as heart rate goes up, stroke volume remains relatively flat in an untrained individual. However, it continues to go up in a trained individual. And just to give you an idea, we'll just say this is 120, and we'll say this is 180. This is a stroke volume that's 50% greater, okay? And so there's two ways that we can do that. We can contract harder, and or we're filling up the heart more before we have contraction. And so that's going to be key. How can we cause more filling prior to contraction? All right, so essentially this, in words, kind of the last couple of slides, stroke volume will increase up to about 40 to 60% of max. After that, it plateaus, maybe even drops slightly. But if you're a highly trained kind of elite level athlete, it's constantly increasing. All right, and this increase in stroke volume is dependent on two things. One, how hard your heart is contracting, which is this contractility, and then that Frank-Starling mechanism, which is preload, or in other words, how much blood is in your heart before contraction. The faster your heart beats, the the less time there is to fill it. So we've got to figure out a way to get more blood in our heart in a shorter period of time. And so we'll talk about that in the coming days.